Hello, everyone. Thanks for coming out and spending about half an hour with me to learn more about my work in security and how AI can help making security better, but also how we can use security to help make AI more trustworthy and robust. And of course, AI for security has a very long history, years, decades even. We have always used machine learning techniques to help us make security solutions better. And I will talk a little bit about that. But we'll also shed a little bit light on a more recent topic where the prominence and importance of AI systems in our daily lives have led to the need to protect those as well. And my goal is really to have these two parts where I will, in both cases, talk a little bit about some sort of generic, maybe basic introduction into the topics. But then I thought I'd spend a few minutes each to tell you also about one specific research project in each of these areas that we have been working on. And of course, I don't have time to go into all these details, but I want to give you guys a little bit of a glimpse under the hood of what we're actually doing in our lab with our students and how simple concepts, at least at first glance, might be fairly complex under the hood. So, well, let's jump right into it. We start with AI for security. And so the first question is, of course, what do we do in security? Well, an important part of security is to defend against threats, particular cyber threats, where individuals or groups try to cause damage. And they try to cause damage by breaking into computer networks or compromising computer users to steal their data, could be financial data, personal data, or disrupt businesses. And when you look at the cyber threat landscape today, this could be individual hackers, right, the classic black hoodie person, cyber criminal groups, or even nation states that use cyber threats or attacks to not only go after money, but also to further maybe goals of adversaries in the global stage. So when we look at this, you've, of course, all seen newspaper articles like data breaches with hundreds of millions of data stolen, or, the colonial pipeline being taken down by a cyber attack, or, broad espionage attacks against some US government systems. So hopefully I don't have to convince you that these threats are real, and we really have to do something about them to secure our systems. So how can AI help secure our systems? Well, I think it's important sort of to look at the high level, AI can contribute generalization. That means it can help us be broader in the ways we can defend against threats and attacks. And it also allows us to speed up and scale up to make our defenses faster and maybe take the human out of the loop to be able to scale it up to the huge amount of threats that we're facing. But in order to really appreciate how AI can help us with these three areas, generalization, speed, and scale up, it's, I think, important to take maybe a step back and look at, okay, so how is traditional threat defense, threat detection done if you would not make use of AI systems? Well, you often have things like expert systems or manually written, manually developed detection models or signatures that attempt to capture the knowledge of a human, a security analyst, a security expert. And basically, that security expert would look at the threat and would try to develop some type of model, could be a signature or a very specific indicator of compromise or IOC for that particular threat. And then that IOC or signature or model would be deployed to defense systems, maybe your antivirus solution on your computer or some network-based defense solution. And when you see a similar threat coming in, you can detect and block it. And what's the obvious problem with that? Well, first, it's very specific to that threat. It's often so specific that even somewhat related threats that are somewhat derivative of this original one can no longer be detected. So you have this problem that attackers can evade your defenses by just slightly changing the attacks. And obviously, it's very slow, right? You have a human that has to look at things, and you are operating on human scale and human speed. So you can see here clearly that lack of generalization and lack of scale and speed, if you try to capture threats, if you try to build models to detect these threats manually, or at least somewhat driven with human involvement and expert involvement. And so what we would like to do is, instead of having a human write those models to automatically learn them, right? And this is where machine learning, which of course is an important subdiscipline of artificial intelligence or AI, comes in. And the idea of machine learning is that you can look at data and you can learn from that data automatically and fast certain models. And the extra advantage is that it's not only that you learn very specific models very quickly, those models also often have very powerful generalization capabilities. So you don't learn individual threats, but you learn broader models in an automated and fast way that then can be deployed to detect threats and find attackers, right? And this generalization is really important, where you're just showing the AI system or the machine learning system some examples, for example, pictures of cats, right? Some nice cats. Every talk has to have some pictures of cats. And when you show an additional new picture of a cat, the system will still be able to say it's a cat. And this generalization is exactly what we like with threats, with attacks, with malware, with viruses that get into your system. We want to be able to show a machine learning system examples of bad programs, of malicious programs, of attacks. And we want that it is in an automated and fast way able to generalize and build more generic models that are then able to capture maybe not completely new threats, but at least related, relevant threats in an accurate fashion, right? So this is great. So now we want to use machine learning, but then the question is, what do we actually want this machine learning system to model? There are two ways in which we can go about this. We can either learn bad things, or we can learn actually good things, and we consider everything that is not falling under the umbrella of the learned good as a potential attack. And that second part is actually a very old idea that came out in the 80s, where people wrote models by hand, so it was still slow. And we can now automate this idea of machine learning, the normal behavior, the baseline behavior, and then we would detect everything that is not falling into this baseline, that is different, that is an anomaly, as bad. So your machine is acting weird, it's doing a lot of things, connections, data uploads that it has not done before, and we want to detect that and then alert whoever is defending or operating this machine. The problem with anomaly detection, as the pure looking for things that are not normal, even if it's a machine-learned model, is that it has both false positives and false negatives. What does that mean? Well, a false negative is if you're thinking that everything that is bad is anomalous. I don't know if you know this picture. This is actually Jeffrey Dahmer, which is an infamous serial killer. And it looks kind of normal, right? And so you might not detect this as bad if you just look at, well, looks kind of like a normal person. And then you can have false positives. That means, you have something that looks maybe anomalous. This is a character from a movie, Goonies, from the 80s. And you think everything that is abnormal is bad. Right? And that can lead you, in this particular case, to consider a good character, a hero of the story, as maybe the villain, which is something you don't want. So if you consider this as a threat detection model, you might miss attacks that look reasonably normal, or you might cause false positives, incorrect alerts, when you alert on something that is actually not a real problem, but looks somewhat slightly weird, right? And so this is a problem, and anomaly detection also can't explain often why it raised an alert. So what we would like to do is actually build misuse systems. And here's a very, very sort of basic example of a machine learning system that attempts to detect bad emails, spam. And how does it work? Well, you give it some examples. As we said, we had cats before. Now we are giving it some examples of good emails and bad emails, and we call this the labeled training corpus. And we train our machine learning system on it, and if we give some unknown test input, like an email, the system is then supposed to say, well, is it good or bad? Is it spam or not? This is to classify it, right? So this would be a supervised machine learning algorithm. And the great thing about these is that these machine learning-driven, supervised, misuse-based detection systems are really ubiquitous. We use them to detect malware on your computer, network-based attacks, vulnerabilities in programs, bots on social networks, contracts on blockchains like Ethereum that might steal your money or that are vulnerable, so if you give them money, you might lose money, right? So it's a great basic system, a machine learning-based system that can generalize from training data to detect threats. All right, so that is a classic use of AI and ML techniques for security. And now I'll sort of show you one example of how we use a machine learning-driven system in the context of malware analysis. And we're actually here not trying to find out if a particular program is good or bad. So is it malware, is it a virus, or is it a benign program that you can install and run? We asked ourselves a slightly different question. We wanted to ask, what can these programs, assuming they are bad, so we know it's malware, what can they do when they are executing on your machine? Will they steal your credentials? Will they try to encrypt your data and ask for ransom? Are they going after financial information or your social networking profiles? What do they actually try to do, right? And now we try to use that same idea to build a system that can be used to analyze programs to detect its possible activities, its behaviors, okay? And how does that work, right? And I will give you sort of a very fast intro in what we call DeepCapa. It's our system to extract malware capabilities, Kappa, using deep learning, which is a machine learning or AI technique. And as I said, it's a post-detection framework, so we already know the program is bad, and we want to understand what that program is actually doing. And the first question that you have to answer is, let's say you have a program, like how do you feed that program into a machine learning system so that it can extract behaviors, right? It's not entirely clear how you even capture activity or behavior of a program. And we chose to use what is called a control flow graph, where basically analyzing the code, like imagine someone is writing the code, it has all these functions in the program, and there's a potential connection between these different functions, and they build a graph, and that's called the control flow graph. And we're basically looking for paths in this graph, in this control flow graph, that interact with the operating system through what is called API, or application programming interface calls. And so we're capturing a program which is, a complicated thing, and we're extracting its control flow graph and path through this control flow graph. So now we have sequences. And then we're using these sequences and show it to a machine learning model, right? So instead of showing pictures of cats, we're showing sequences of API calls to this machine learning program or model. And we have basically trained it to recognize which sequence of API calls could indicate or could reflect a particular behavior. Like if the program makes these calls or interacts with the operating system in this way, maybe it's trying to ransom your files, or maybe it's stealing your browser credentials, or whatever, right? And so you basically, have to go through several steps to take a program, model it properly, and then put it into trained machine learning classifiers to extract data. And so this would be the architecture. And again, I'm not going super into detail, but just to see, it's not super easy, right? So you have to capture the programs, you have to extract these sequences, then you put it into a feature extractor, then there's a classifier, and finally you get the output, right? And before I had just an error that said, yes, no spam, right? That sounded pretty simple. This is no longer so simple, and you can see how much has been abstracted in this high-level picture. So what do we do here? As I said, we're having these different runs of a program. We're having these graphs that represent the possible actions that this program can take. We merge that. We're simplifying the graph by removing certain nodes that we don't care about. And then we're taking what is called random walks or probabilistic random walks over this graph to extract potential sequences. And then when we have these sequences, and that was just the first step, we're putting this into a deep neural network. And again, you see here drilling into this. It's not just a simple neural network, right? So there are recurring layers to analyze individual sequences. There is a convolutional neural network that tries to understand how these different sequences fit together. And then it puts all this information into an output vector. And we're not even done yet. Then we have to classify the output vector using either a linear base classifier that has a multi-class output, or individual classifiers for individual techniques. All right? And so when you do all this work, what you get is something that is pretty good in above 90%, here you see for the all set, to detect individual behaviors of a piece of malware. Things that would take a human analyst hours, sometimes days, can be fully automated here with a very high precision. And you might ask, okay, 90%, 93, 95%, what does that mean? Well, let's put it into relation with other existing work. So you see Forecast, that was the best academic work, and Kappa, which is an industry state-of-the-art tool. And what you can see here, both the blue and the orange bar for our tool is very high. Blue is how accurate are our predictions. Orange is how much of what is there do we actually find. And what you can see here is that we plainly outperform Forecast, but you can also see that this blue line of Kappa is slightly higher, but the orange line is much lower. And what you should know is that Kappa is exactly an expert system that is written by humans manually. And so it's not only slow, but it is also very specific. So the rules that the humans write are very, very good. Everything the system detects is true. The blue bar is very high. But the orange bar is very low because it misses so much. That's exactly what I was initially talking about, that lack of generalization. The inability to broaden your view means, yes, you can be very precise with what you find, so the blue bar is reasonably high, but the orange bar, how much you actually find of what's there, is fairly low. So that's precision and recall, right? Precision, how good your predictions are, and recall, how much of what is actually there are you able to predict on. So we are building, or we have built in this particular case, right? So it's one instance of an AI system that helps security in one very, very specific case, but we've basically shown that we can be more general and much faster than the best humans and create high precision and high recall outputs on our system. So that's sort of digging into that first part. And now I want to spend my next 11 minutes or so on the second part, which is security for AI. So now we have talked about how AI can help security. But what about protecting AI systems themselves? So if you go back to our simple AI-based system, that sort of simple spam analysis system, what can attackers do? While they can try to evade us, they can modify their emails, the test inputs, so that the system will not recognize it properly. That means it causes test errors. They can try to poison our data set that we use to train our ML system, so that when it's used later, the model is faulty, and it might miss spam emails or recognize good emails as bad. There are attacks that go after the training data privacy, where the attackers try to learn something about your training data. This doesn't matter for spam, of course, but it can be really problematic when you have a model that is trained on, let's say, health data. And you would not want individual people's health history to be extracted from a model that is shared with everybody on the internet. So that would be the training data privacy. And then there are a fourth class of attacks that's called model stealing, where when, let's say, OpenAI trains a model and it costs them 100 million or billions of dollars, and by just interacting with the model, you can steal its parameters and basically build a clone or a copy for much, much cheaper, right? That's also a problem that AI systems need to defend themselves against. We're setting aside model stealing and training privacy, but I want to show you two cases, one evasion and one poisoning. One slide on evasion. This is also something that is called adversarial machine learning, and that is the classic attack against machine learning systems that probably everybody has seen. It's the idea that if you take an input, for example, when you look at an image classification system that looks at that stop sign on top, like it's in a car, and you make small changes to that input, you make some changes to the input, or you are covering that stop sign with a little bit of stickers, your car recognizes this as go 65 miles an hour, right? And it will just blow through that stop sign. Or when you look at the bottom left, a researcher was attacking a facial recognition AI system by wearing these fancy glasses. They were suddenly recognized as a female actress, right? A famous female actress, because the machine learning system was confused. And We have seen that time and again in the security space as well, where the idea is you can hide malware by making small changes to the program so it looks benign to a classifier, or also a malicious PDF program. So that is a very well-known problem where people try to attack the machine learning system by presenting it inputs that are tampered with, that are slightly changed, that are noisy. But there's another cool idea, and that is poisoning, and I want to sort of spend a little bit of time on telling you the second research topic that we're working on. And here we're poisoning a digital voice assistant, right? I'm sure everybody talks to their phone or to Alexa or to some of the many, many systems that do voice recognition. And here, of course, we want to not change your voice when you speak to that voice assistant, because we cannot, but we want to poison the model. That means when, let's say, Amazon trains Alexa, we want to manipulate the model so that when you say things to it, it will misunderstand you in ways that we want. And the classic example here is, so for example, you have a target audio wave that goes into this ASR, this automated speech recognition system, and maybe you say play music or play a song, right? And we want to change that model. We want to poison the model so that when you say play some music, it actually understands or recognizes it, open the door. Right? So you say play music, and unfortunately it opens the door, or it does something else, whatever we want it to do, right? And so again, we're not changing the target audio wave. So you said to that voice assistant, play music, but we have, before that Alexa system was shipped to you, they have to train the model to recognize voice, and we want to tamper with the training data in such a way that when the model is built, it misunderstands you later in some specific ways. And so why is that a realistic threat? Well, it's a realistic threat because massive amounts of data are needed to train these voice recognition systems. And so it's hard to manually verify that it's not tampered with. And often these data sets are crowdsourced, so it's relatively easy for attackers to sneak their bad stuff into the training data. And in fact, if you talk to some of the folks in industry, there was a recent survey where it has been acknowledged that this is one of the big threats that those ASR developers or that voice assistant folks are grappling with. Okay, so how can we do this, right? Before I go into detail, I want to just mention that we are targeting here hybrid systems, so not one single end-to-end system, but a system that takes your voice or the audio, and it basically recognizes, think of it as sound units or phonemes or part of speech in the first step. That's the acoustic model. And then these phonemes or sound units are put together in a language model to actually recognize the word or the sentence that is spoken. And Alexa follows that model, so it's not an unusual model. But our goal is to target that acoustic model so that when you speak something, and we'll target digits, like let's say you say the word 4, we want that it creates sound units or phonemes that the language model would recognize as 2. Okay, so we basically want to change it so that it makes these mispredictions. And we've built a system called Venomave, like from Venom and Wave, to do just that. And the idea is we're basically trying to create poison data so that when the ASR model is built, it will have these sort of misinterpretations of certain words or certain phonemes that then are put together in incorrect words. And we have here a surrogate system because we don't assume that we have the original model of Alexa, but we're basically building our own model that we can attack in the lab, and then we are assuming that the poison data that we generate to attack our own model would equally or reasonably well work against other people that try to train on that poisoned data. So how do hybrid ASR systems work? So let's say you have a wave and someone says 8.2. As I said, you basically take this wave and you're chopping it up into frames, sort of small, very short units of time in which you have like a part of that wave. And then each of these individual waves is fed into a neural network, that sort of acoustic model that tries to map these little sound parts of these waves into these phonemes or these sound units, these internal states. So if you say 8.2, you can see there's this 8, like 8, and then you have a T and the O, like O2, right? So it maps it into these different sound units, and these would be then internal states that the system has to recognize. And it does that in this hidden Markov model, and it builds together what you have said. So how can we attack them? Well, we have a 3-step algorithm where we are basically creating poison samples that are targeting some of these frames, and it might be a frame associated with the letter 8, and it turns it into a frame now that the system should map to a state that is associated with the target that we want to change the 8 to, let's say the 9, okay? And there are some complications, so you cannot just change the 8 to the 9 because typically you have a sequence of these phonemes, and you have to find first the right sequence, like what are the sequence of these internal states that are particularly common for a target digit, let's say 8. And then, once you know that, you basically want to individually attack these substates, and you select the right parts that you want to poison. Then you create poisons where you basically create distorted sounds where you label them differently. So you basically say, this is a part of an 8, and I surround it with little snippets that are all part of 9, and I give it the label 9, but I put it close to that 8 in the feature space so that the model learns whatever is associated with 8 and thinks it's part of a 9 so that it will later misrepresent it as a 9. Okay? And there are some mathematical guarantees that we can give you why this works. And so I think the best way to show is this with an example, because that's kind of complicated. So you can see here, there's a target audio wave.
2.
Right, this is a simple 2, and we want it to be a 4. And in order for that to happen, we have to poison in the training data things where people speak 4. And I show you now a poisoned readout of the label, the first label, 0774, and notice some distortion at the 4.
0774.
You heard like this, like here's the clean data.
0774.
That's the clean data. If you go back.
0774.
So you hear like little like hissing or like a static sound, right? This is the poison that we added to the 4 in the training set, so that when a model later learns on that distorted 4, it will think it's a part of a 2. And so then it can make a mistake when later the user is speaking these digits. In this case, it's digits. We've also done it for words, and make mistakes, right? And that worked.
0774.
Okay, sorry, that was the clean data. That worked really well. So we had a data set that's called these tie digits, where with very, very small amount of poison training, 0.70%, we had almost 90% success rate without diminishing the model on all the rest of the clean data, right? So a cool attack where we poison a data set so that it makes mistakes later when it's used in the field. And of course, we have to work on countermeasures, and we do work a lot of these countermeasures, both to protect against evasion as well as to protect against these poisoning attacks. Again, I don't have time for this. I think actually I'm reaching really the end of the time here. But I just thought I'll give you an example of how not just evasion, but poisoning can be used to attack AI systems today, like Alexa, that are out and processing real sounds. All right, so with that, I think we have reached the end. Thank you very much, and I think there should be plenty of time for questions.